All right, now let's continue on. And as we said in a previous lecture video, there are three types of probabilities. We have classical probabilities, which are the probabilities that you've probably used up to this point in your learning and classes. Classical probabilities are typically used when we think about things like rolling dice or flipping coins, games of chance in general. The second type of probability is relative frequency probability. And then the third type of probability is subjective probability. So since you are fairly familiar with classical probabilities, we're going to spend a little bit of time in this lecture video talking about relative frequency probabilities and subjective probabilities. And so let's talk about relative frequency probabilities first. Okay, so we need to define what a relative frequency probability is and kind of set the stage for this. So first, consider a sequence of n identical experiments or trials. Then we're going to let A be some event of interest, the probability of which we are interested in obtaining. And then we're going to define the following notation. So corresponding to the event A, we're going to denote a symbol A sub n, and we're going to let that denote the number of times out of the n experiments that the event A occurs. All right, so we would perform this experiment or the process n times, so we have n trials, and the number of times that the event A has occurred is going to be denoted by cap A sub n. Now, with that, what's called the relative frequency of occurrence of the event A in the n trials is then given by the ratio of A sub n over n. All right, so it's just the proportion of times out of the n trials that the event A occurs. Now let's consider letting the number of repetitions of the experiment, denoted by n, increase without bound. So we're going to let n go to infinity. Then the probability of the event A is then defined as the limiting value of this relative frequency. All right, and so the probability of A is denoted by this P of A right here, and it's defined to be the limit as n goes to infinity of cap A sub n over n. So the limit as the number of trials goes to infinity of the relative frequency, or the proportion of times that the event occurs, assuming that this limit exists. So in order for this to make sense, that limit would have to exist, and when it does, that represents the probability, it represents the relative frequency probability of the event A. So that is how we define relative frequency probability. It's the limiting value of the relative frequency as n goes to infinity, as the number of trials goes to infinity. And so, for example, if we were thinking about the relative frequency probability of flipping a head with a given coin, then we can think of a sequence of coin flips with that coin, and then the relative frequency that we would be talking about would be the proportion of times out of n trials that we get heads. And then if we think of extending that sequence of trials out into infinity, to an infinite number of trials, then and if that limit exists in terms of the relative frequencies, then that would be what we're calling, or what we're defining to be, the relative frequency probability of getting heads with that particular coin. And note that if the coin is biased in some way, if it's bent or something like that, then it may be the case that the relative frequency probability of getting heads with a particular coin is not 0.5. It could be something else. It could be 0.52 or 0.46. All right, so it may not be obvious just by looking at the coin whether or not it's fair. In other words, whether or not the probability of heads is 0.5. All right, and so if we think in terms of relative frequency probability, then we have this possibility that that the probability of heads may be something other than 0.5. if we were using classical probability, then assuming that we could not see any differences or any oddities about the coin, we would probably just assume that the probability of heads was 0.5. Okay, so now that we've defined relative frequency probabilities, let's talk about properties of relative frequency probabilities. If you remember, we made the statement back when we first talked about relative frequency probabilities in a previous lecture that properties of relative frequency probabilities can be mathematically derived and mathematically proven. And so here are some properties that relative frequency probabilities possess. And so let's set the stage by defining some notation for some events and probabilities. So let A and B be events with corresponding probabilities, and in particular corresponding relative frequency probabilities, P of A and P of B. All right, so again, these are based on the relative frequency approach. Then the following properties hold. They can be derived mathematically, actually. So the first property, which I'm calling RFP1, relative frequency property 1, is that probabilities, relative frequency probabilities, are always between 0 and 1. All right, they are greater than or equal to 0 and less than or equal to 1. Now that may seem like it's obvious and that it ought to be true, and that's good. When we think about classical probabilities, whenever you have calculated a classical probability in previous courses and things like that, you always got probabilities that were between 0 and 1, as long as you did the calculation correctly, right? So this seems almost too obvious to state, but the reason I state this is because, this is a theory class, and the purpose of the class is to prove the things that we talk about. And so we're going to look at a proof of this, all right? But I do want you to think about how you would go about proving it. Okay, so the second RFP, relative frequency probability property 2, is the following. If the occurrence of the event A implies the occurrence of the event B, then the probability of A can be no more than the probability of B. Or in other words, the probability of A is less than or equal to the probability of B. All right, so think about what that means. All right, and also think about how you might go about proving this. Now, let me just say that when you prove a relative frequency probability property, then in many cases, and probably in most cases, I will ask you to prove these things in the context of relative frequency probability. So in other words, using the definition of relative frequency probability, and then any other properties that you've already proven. All right, so that's how the game is played. When we're proving things mathematically, we have to use the definitions and any axioms that we might have. And then if we've got any other properties or theorems that we've already proven, then we're free to use those as well. But anyway, in proving these properties, we would have to utilize the definition of relative frequency probability. Okay, RFP3, relative frequency probability property 3, says the following. Now, before I read this RFP, let's look down here in the following two lines. We need to define this notation. So I've got what we might call a wedge and a hat, okay, notation. This wedge notation, this is the logical disjunction, all right? What this means is that either A or B occurs, okay? A is an event, B is an event, and so this together is an event, and it's the event that either A or B occurs. And when we say or in this sense, we're talking about the inclusive or. So it could be that they both occur as well. Now, another way to say this that makes that a little bit clearer is that this A and then logical disjunction B, we can read this as at least one of A or B occurs. All right? And then this symbol is the logical conjunction, so it means and, right? So this wedge means or, okay, and this hat means and. And so this is the event that both A and B occur. All right? So with that notation, then RFP3 says the probability that at least one of A or B occurs is always going to be equal to the probability that A occurs plus the probability that B occurs minus the probability that both A and B occur. All right, so that is RFP3, and this is always going to be true. All right, this is, and we're specifically talking about relative frequency probabilities. So in the context of relative frequency probabilities, this equality will always hold. Now, you may have seen a similar equality in the context of classical probabilities. And so what this would show is that we have a property that is common to both, another property that's common to both classical probabilities and relative frequency probabilities. In fact, now we have three because these first two RFPs can be shown to be true for classical probabilities as well. All right, so anyway, we've got three properties here that are common to both classical and relative frequency probabilities. Now on to RFP4. If A and B are mutually exclusive, in other words, if they cannot occur at the same time, then it turns out that the probability that at least one of the two events occurs, A or B, is always going to be equal to the sum of the probability of A and the probability of B. All right, and so again, the assumption here is that A and B are mutually exclusive. They cannot occur together. All right, and so this is actually a special case of RFP3. All right, where because A and B are mutually exclusive, the probability that they both occur would be 0. And so that's why that drops out. Okay, then on to RFP5. For any two events A and B, the probability that that at least one of the two events occurs is always going to be less than or equal to the probability that A occurs plus the probability that B occurs. All right, so that is always going to be true. And then RFP6, and this is a very important result. We've actually already used the result of this RFP in previous work, in a previous lecture. So the sum of the probability that A occurs and the probability that A does not occur, or in other words, the complement of A, is always going to be equal to 1. So in symbols, what this means is that the probability of A plus the probability of A complement will always be equal to 1. And so what we can do then is take this relationship, we can take this equation and solve it for the probability of A complement, the probability that A does not occur, and what we get is that the probability that A does not occur is equal to 1 minus the probability that A does occur. All right, and that result is called the complement rule. Okay, now I want to go through the proofs of at least one or two of these RFPs. And so let's look at the proof of RFP1, which says that for any event A, the probability of A, the relative frequency probability of A, is always going to be between 0 and 1. All right, now the proof goes like this. Recall that cap A sub n is the number of the n experiments in which the event A occurs. All right, so A sub n is a counter counting the number of times that the event A occurs in the n trials. And so it's obvious, it's clear that the number of times that the event A occurs has got to be greater than or equal to 0, and it can be no more than n, right? And this is for every n going from 1 and on out, okay? So these relationships hold for every natural number n. Now, if we take that set of relationships and divide everything by little n, all right, and because little n is positive, the direction of the inequality stays the same, then what we get is 0 over n, which is just 0, is less than or equal to cap A sub n over n, which is less than or equal to n over n, which is 1. Okay, now cap A sub n over n, that is the relative frequency of the occurrence of the event A out of the n trials. And now what we're going to do now, well, let me just say that we can see that this relationship holds, this set of relationships holds for every n, okay? The relative frequencies, the relative frequency of the occurrence of the event A is always between 0 and 1 for every n. And so when we take the limit as n goes to infinity, then what we have then is that the limit as n goes to infinity of these relative frequencies is also going to be between 0 and 1. But now, what is this thing here in the middle? What is this limit? Well, that, by definition, is the relative frequency probability of A, assuming that it exists, assuming that that limit exists. And so what that then implies is that the probability of A, the relative frequency probability of A, is going to be equal, or I'm sorry, between 0 and 1. And that's what we set out to prove. So that is how we prove RFP1 using the definition of relative frequency probability. Okay? Let's look at RFP2, see if we can prove that. RFP2 says that if the occurrence of the event A implies the occurrence of the event B, then the probability of A can be no greater than the probability of B. In other words, the probability of A is less than or equal to the probability of B. And so how do we prove that? Well, let's define some notation. Right? The first thing we've got to do is define notation. And we're going to let the result that we're trying to prove guide us in what notation, what sets are we talking, I'm sorry, what events are we talking about, and what counters then do we need, and we'll then need notation for those counters. So this RFP involves events A and B and their probabilities, and so we need some counters. We need to define counters for the number of times that A occurs and the number of times that B occurs. And so I'll let cap A sub n be the number of the n trials in which the event A occurs. And likewise, I'll let B sub n be the number of the n experiments in which the event B occurs. Now, if the occurrence of the event A implies the occurrence of the event B, then the number of experiments in which the event A occurs can be no greater than the number of experiments in which the event B occurs, since B occurs whenever A occurs, but B may occur without A occurring, right? So if A occurs, we know that B must occur because A implies B, the occurrence of A implies the occurrence of B. And so again, what this implies then, this relationship in terms of the counters. All right, so the number of times that A has occurred out of the n trials can be no more, it's less than or equal to the number of trials in which B occurs. So we have this relationship between the counters that holds for all n, all right? And so then what we can do is we can divide both sides of that inequality by little n, and because n is a positive, we don't, or the direction of the inequality stays the same, and so that means that for all n, a cap A sub n over little n is going to be less than or equal to cap B sub n over little n. And so, what this is saying is that the relative frequency of the event A is going to be less than or equal to the relative frequency of the event B, and that's true for all n. And because it's true for all n, when we take the limit as n goes to infinity, the limit of cap A sub n over n is going to be less than or equal to the limit of B sub n over n. Now, the left-hand side, this is just the probability of A. And the right side is the probability of B. And so we get our result. The probability of A is less than or equal to the probability of B. So that is that's the end of this proof. And we're going to now jump to a few notes on subjective probability. All right, so I just have a few questions that I want you to think about regarding subjective probabilities. Remember that we said that subjective probabilities are personal probabilities, and there's no really real way to quantify or qualify or prescribe how we come up with them. All right, and that's because they are subjective. And so, but the question is, how are subjective probabilities determined? And if you think about your own situation, how do you come up with subjective assessments regarding the likelihood of events? And there are probably a multitude of ways that you would do that using a variety of kinds of information and differing amounts of information in different situations. Now, another question is, because we just got done showing that relative frequency probabilities have certain properties that we can prove mathematically, and in particular prove using the definition of relative frequency probability. The question I would ask for you to think about is, what properties do subjective probabilities possess? Now, in looking at the RFPs for relative frequency probability, I said that those properties are those are properties that classical probabilities have as well. And so the question is, do subjective probabilities share those same properties? So I want you to think about that. The follow-up question would be, if you believe that a subjective probability has a certain property, how would you go about ascertaining that? But how would you prove it? All right. And so how would you prove the property that you believe subjective probability has? Now here's another question: can a subjective probability be wrong? Right? If it's your own personal assessment of the likelihood of some event, can that be wrong? I mean, so for example, if you say that your subjective assessment of the probability that it's going to rain today is 0.4, if I were to say, well, that's wrong, it's some other value, is there any justification for me saying that? I mean, I may have a different subjective assessment, but does that mean that your personal assessment is wrong? I'm not sure that that would be valid for me to do that, right? So anyway, that's an interesting question to consider. Can subjective probabilities be wrong? Now, here's another question. Is it permissible to mix different types of probabilities, say probabilities of the subjective type and probabilities of the relative frequency type, in a single calculation? So as you'll see, we're going to be doing some mathematical calculations and using formulas that involve two or more probabilities in many situations. And the question is, can we combine probabilities in those calculations that are of different types? All right, and if we can, right, if different types of probabilities are mixed in a calculation, then what is the resulting type? So for example, if we combine a relative frequency probability and a subjective probability in some kind of a calculation, maybe we add the two or take a ratio or something like that, then what is the resulting type? In other words, is it a classical probability? Is it a relative frequency probability? Is it a subjective probability? There are only three types of probabilities. So if it's legitimate to combine or mix probabilities of different types in a single calculation, then the resulting, and coming up with another probability, then the resulting probability has to be one of those three types. So what type would it be? In addition, what properties does that probability possess? All right. And in addition, how is such a probability to be interpreted? What is its connection to reality? Right? How do we interpret that value that we've come up with by combining two or more types of probabilities into a single calculation? We know that we have meaningful ways of interpreting a classical probability. We know that we have meaningful ways of interpreting a relative frequency probability. All right. we understand the connection to reality because, for example, in the relative frequency probability situation, we defined the relative frequency probability as the limit of the relative frequency of occurrence of the event as the number of trials goes to infinity. All right? And so in a very large number of trials, we might expect that approximately, or that the proportion of times that the event occurs is approximately equal to the probability. All right? So that gives us a way to interpret what that relative frequency probability represents. What is the interpretation, what is the connection to reality of a probability that's obtained by mixing two or more types of probabilities? So those are some interesting questions to consider. So that is the end of this lecture video. In the next lecture video, we're going to continue on looking at a modern approach to the development of probability theory called the axiomatic approach to probability theory.